So good morning, everyone, and welcome to today's webinar in the CERTIP and ESTCP webinar series. My name is Mike Cavanaugh. I'm a Senior Principal Chemical and Environmental Engineer at Geosyntec Consultants in Oakland, California, and I'm the co-coordinator and facilitator of today's webinar on behalf of CERTIP and ESTCP. I'm channeling my colleague, Dr. Rula Deeb, who usually does this work. Our agenda for this seminar today, the webinar today, is shown on this slide. Will consist of a brief overview of CERTIP and ESTCP by Dr. Robin Neeson, followed by a list of upcoming webinars in the series. And after Robin's opening remarks, we'll transition to the technical portion of the webinar. Today's event features two presenters who will talk about an environmentally acceptable alternative for fast Cookoff testing, demonstration, validation, and implementation efforts funded in part by ESTCP. First, we'll have Dr. David Hubble from the Naval Surface Warfare Center, Dahlgren Division, who will discuss the design and calibration of the propane burner, followed by a short Q&A session. Second, we'll have Dr. Ephraim Washburn from the Naval Art Warfare Center, Weapons Division, and he'll provide an overview of the energetic and inert items test results, followed by a final Q&A session. We'll conclude the webinar with an interactive Q&A session with both speakers. Today's broadcast will be listen only. You may submit questions by using the chat box on the left-hand portion of your screen. You do not need to wait until the Q&A period to submit your questions. In fact, we all encourage you to submit questions in advance of that session. On this slide, the next slide, we have provided a few suggestions in the event that you experience difficulties with the broadcast audio. This has not happened, but we're trying to be safe here. Typically, any delay will be fixed if you refresh your screen or call into the conference line. However, if you continue to have problems, please submit a comment using the chat box in the lower left-hand corner of your screen. And with that, I'd like to introduce our two speakers today. Dr. Robin Neeson, who is the CERTIP and ESTCP Program Manager for Weapons Systems and Platforms. Before joining CERTIP and ESTCP, Robin worked at Navar's Weapons Division, China Lake in California. So Robin, let me turn it over to you.
Well, thank you, Mike. I'm very pleased to welcome everyone to today's CERTIP and ESTCP webinar. CERTIP is the Strategic Environmental Research and Development Program and was established in 1991 by Congress as a partnership between DoD, the Department of Energy, and EPA. CERTIP's mission is to identify and address high-priority environmental science and technology opportunities that focus on DoD requirements. CERTIP funds both fundamental research as well as advanced technology development that ultimately impacts real-world environmental management. ESTCP, the Environmental Security Technology Certification Program, was established to demonstrate innovative environmental and energy technologies. These investments capitalize on past investments under CERTIP or other research programs and are designed to transition technologies out of the laboratory and into the field. Especially important in all ESTCP demonstrations is the ultimate transition to implementation and regulatory acceptance. CERTIP and ESTCP are complementary programs, and much of the CERTIP efforts occurring at the laboratory and pilot scale, but with occasional field efforts. CERTIP, on the other hand, is demonstrations that are primarily at the pilot and field scale, although occasionally there are supporting laboratory efforts that are conducted. We have 4 program areas in CERTIP and 5 program areas in ESTCP. Energy and water is an ESTCP-only program area, while the other 4, environmental restoration, munitions response, resource conservation and climate change, and weapon systems and platforms, cover both CERTIP and ESTCP. and programs are managed jointly by one designated program manager in each of those 4 program areas. Today's webinar is focusing on research and demonstrations that were conducted under the Weapon Systems and Platforms program area. And this program area has 5 major focus areas: surface engineering and structural materials, energetic materials and munitions, noise and emissions, waste reduction and treatment in DoD operations, and lead-free electronics. Actually, today's topic is going to cover a little bit of energetic materials and munitions, as well as emissions. Future webinars. Our webinar series will be highlighting research and demonstrations efforts from each of the 5 program areas. And as you can see, our webinars cover a broad range of topics, with upcoming topics covering the assessment of redox-based groundwater remediation technologies, cybersecurity requirements and impacts on installation energy systems, and DoD decision-making regarding climate change. I also see the brown tree snake there too. So here you go. You can find more information about our webinar series at the link provided, and registration is now live for several upcoming events. With that, I hope you enjoyed today's webinar. Back to you, Mike.
Thanks, Robin. So our 2 speakers today, their pictures are shown on the slide, and our first is Dr. David Hubble, who works in the Instrumentation, Science, and Technology branch at the Naval Surface Warfare Center, Dahlgren Division in Dahlgren, Virginia. Since starting with the Navy in 2013, Dr. Hubble has worked on all aspects of insensitive munitions testing, but is primarily focused on developing an alternative to the liquid pool fire used for fast cook-off testing. As part of this effort, he has been involved in the Fuel Fire Experts meetings, which are international meetings involving the world's experts in fuel fire testing. Prior to starting with the Navy, Dr. Hubble spent time working in industry on advanced instrumentation for aerospace applications. He earned a bachelor's degree from the University of Tennessee in Knoxville in 2006 and a PhD in mechanical engineering with a focus on heat transfer from Virginia Tech in Blacksburg, Virginia in 2011. Our second speaker is Ephraim Washburn, who joined the Energetics Research Division of the Naval Air Warfare Center Weapons Division in 2004. His research focused on modeling and simulation of various forms of combustion, solid propellants, metal, and hydrocarbons. He is currently involved in both modeling and experimentation of fast and slow cook-off. Together with Dr. David Hubble, Dr. Washburn is the co-lead of ESTCP and Insensitive Munition Advanced Development Program projects to develop and validate a propane fast cook-off burner. He is part of an international group working to update AOP 4240 to include instructions on the use of alternative fuels for the fast heating test procedures for munitions. Dr. Washburn received his BS and PhD degrees in chemical engineering from Brigham Young University in 1999 and 2004, respectively. So let me turn it over now to Dr. Hubble.
Thanks, Dr. Cavanaugh. This is Dr. David Hubble here at Naval Surface Warfare Center in Dahlgren, and I'm excited to talk to you all about the work that Dr. Washburn and I have been doing over the last few years on this project. Dr. Cavanaugh gave a pretty good overview of our agenda, but just to recap, I'm going to start with a background of what a fast cook-off test is, why they're performed, and some of the issues with the current test method. Then I'm going to go into details on the design and calibration of the propane burner that we've developed to replace the traditional test method. Then we'll have a short Q&A session before I turn it over to Dr. Washburn, who will go into detail on some test results from energetic and inert items we've tested, and then finally a second Q&A session. Before I start, I want to go ahead and thank the sponsors of this project. The Environmental Security Technology Certification Program and the Insensitive Munition Advanced Development Program have been funding this work for the last few years, and none of this would have been possible without their support. And so I want to go ahead and give them a big thanks before we get underway here. So the fast cook-off test is a standard safety test required for all explosive ordnance, and it's designed to see how these ordnance items react when they're subjected to fast heating like they would experience if they were in a fire. And so a cook-off occurs when an energetic item explodes due to an external heat source. And these tests were initiated in response to some catastrophic fires aboard carriers in the 1960s. The images at the bottom show some of the results from these fires. Notably, the USS Forrestal in 1967 had an incident where 134 U.S. sailors were killed. And what happened was you have a bunch of planes getting ready to fly their sorties. They're loading with explosives, and in any fire that starts on the deck, you start having a bunch of bombs immersed in a large fire. Once one of them cooks off, it's a chain reaction that's hard to stop. So, in response to this, the DoD initiated this fast ground cook-off testing, and the purpose is to gradually improve the IM response, in situ munition response to these items, to make them less sensitive to external heating. You want to work towards a situation where the item does not explode at all. It simply burns or does nothing at all when it's subjected to these kind of incidents. And to perform the test, the test item is immersed in a large flame produced by burning liquid hydrocarbon. As shown here in the bottom left-hand picture, we have a 105 millimeter howitzer round on a test stand sitting in the fuel basin here at Dahlgren. And once the item's in the basin, the next step would be to pump in the fuel required to produce the fire. It's typically either jet fuel or kerosene. And you have to pump in enough fuel to produce a fire that burns 150% or 50% longer than the expected reaction time. So you have to sort of estimate up front how long you think it'll be before the item reacts, and then pump in a bunch of extra fuel because you don't want to be too short. The other requirement from the STANAG 4240 is that the flame temperature measured around the item has to be greater than 800 degrees Celsius for the average duration of the test. There's been a steady and constant push for an alternative fuel that stems from some of the issues with the current test method. First and foremost are the environmental concerns that stem from this test. Lots of atmospheric emissions are emitted from burning these large pools of hydrocarbon in a very inefficient way. You also have the public relations problem of the large black clouds of smoke emanating from the test site that really worries people in the vicinity. It's a very visual indication of how bad the test is. And then the very real risk of soil contamination from either spilled or splashed liquid fuel out onto the ground that's then absorbed. There's also a number of safety and technical risks involved with the test. The fuel is typically transferred to the basin after the energetic item is in place. So now you have workers around this bomb and fuel present all while they're out there. Another problem with that is the amount of time it takes to transfer that fuel can be on the order of an hour, and these tests are very weather sensitive. You can't perform them if there's hardly any wind. So you have to estimate what the wind's going to be an hour from now, and that can cause problems because once you've started transferring that fuel, you've basically committed to doing a test. And so if the wind picks up, you're at a risk of having to repeat that test. And as I mentioned before, you have to estimate how long until the item reacts and pump enough fuel in. So if you underestimate that, you run the risk of not putting enough fuel in and having your fire go out before anything happens. And now you are in a position where you have an energetic item that's been heated, now it's potentially unsafe, and you have to repeat the test. So those are some problems we're trying to address. And on top of that, the cost, a typical test at Dahlgren requires between 1,500 and 3,000 gallons of jet fuel. So just fuel costs alone can run the order of $10,000 for these tests. So with these in mind, there's been an increasing interest across NATO to develop a cleaner alternative. In fact, some countries have already banned performing this liquid fuel test in lieu of a cleaner method. Early on in this project, it was noted that propane offered a number of benefits that could address a number of these problems. Starting with the environmental concerns, propane burns much more cleanly than jet fuel or kerosene, so you have much less atmospheric emissions during the test, and virtually no soot cloud. The propane burns very completely, and you can't hardly even tell that there's any smoke emanating from the fire at all. There's also almost no chance of soil contamination because of propane's boiling point of about minus 40 Celsius at atmospheric pressure. Any spilled propane basically just evaporates and wafts away. From a safety and technical standpoint, one nice thing, you're flowing the fuel through piping to the burner site, so there's never a situation where there's ordnance and fuel at the site at the same time. There's no fuel at the test site until all personnel are in shelter. Also, the fire duration is only limited by the size of your fuel tank, so in theory you could burn almost indefinitely with a large enough tank. And the other side of that is you can turn the fuel off as soon as your item reacts. So you don't really have to estimate how long until your reaction is, and you save all that fuel. If there's an obvious reaction, you just shut the fire off. There's no liquid fuel for your components to fall into, and there's that delay between the go decision and the test initiation is virtually eliminated, because as soon as the test engineer says he wants to test, the fire can be ignited. There's also a significant cost savings. So far, Dr. Washburn will go into some of the details, but we typically use about 1/10 as much fuel for a given test compared to the liquid fuel. So when we started designing a propane burner, there were a number of thermal constraints imparted by the testing standards that we had to meet, and these were condensed down into the following 4 requirements. The flame temperature still must be greater than 800 degrees Celsius. The average heat flux to the item must be greater than 80 kilowatts per meter squared. The heating should be uniform, and the heating should be approximately 90% radiative. And all these are these stem from trying to duplicate the heating that isn't liquid pool fire, which is what is most likely to the item to experience during some kind of incident. Additional guidelines we impose to increase the logistical usefulness of a burner are that it be made from inexpensive, commercially available parts to make it affordable and expendable. If you test long enough, sooner or later you're going to have a high-order reaction that completely destroys your burner. You don't want to be out a whole lot of money. It should be quick and simple to repair in the event that it's damaged. Again, some reactions will damage the burner, and it needs to be easily repaired. And it should be scalable or modular for testing large or odd-shaped items. So this slide shows an overview of the burner that we developed. It's made from as shown in the right-hand picture there, we have a square burner box that's 12 feet on a side, 3.6 meters. And then inside of this we have 12 burner tubes, or 26 burner tubes, I'm sorry. And each burner tube has 26 gas ports in it, so for a total of 676 gas ports that evenly distribute the propane gas within this burner. We also have these side shields. There's only one shown in the picture so that you can see inside of the burner, but typically there'd be a side shield on each side, and these serve to eliminate or reduce the amount of air that is able to get into the burner, which helps us produce the fuel-rich fire like what you see in a liquid pool fire, to more accurately represent the same heating of a liquid pool fire. Some more details of the burner design. The burner tubes themselves are simply 2-inch Schedule 40 galvanized steel pipe, but we actually flow liquid propane to the burner, and then the radiative feedback from the flame is what boils the propane in the tube. So we have gaseous propane emitting into the burner volume, which burns. Using liquid propane was sort of key. It has much higher density than gaseous propane, so it was much easier to get the fuel flow rate needed to produce the size and intensity of flames that we required. Also, since we're flowing liquid propane out of the tank, we don't have to worry about a pressure drop. The phase change is occurring within the burner itself instead of within the tank. So we don't have the problem of tanks frosting up and the pressure dropping as they cool down. So essentially what we've done is combined a fuel vaporizer and a burner into one simple unit. Let's see. The next slide shows a video of our burner in operation. but I'm having trouble getting it to play. Okay, there it goes. Okay, now it's playing. So this is a video of what our furnace is like during the test. These are very that's what the size amount of air into the burner. So you have this fuel-rich flame, lots of carbon soot particles within the flame that get hot and then emit radiation to the item, and that really simulates the same type of heating that you have in a liquid pool fire. So once we had the burner, we had to do a very thorough thermal characterization to determine if it met those thermal requirements that we imposed or were imposed by the test standards. First, we had to determine where the temperature requirement within this burner volume is met. And to do that, we used an array of thermocouples. I'll show details of that in upcoming slides. We also had to see what volume met the heat flux requirement. Simply meeting the temperature requirement does not necessarily mean that it meets the temperature or the heat flux requirement. The heating uniformity, where within this burner volume is the uniformity acceptable. We can look at both the temperature and heat flux measurements to determine that, and we also want to see where the heating is primarily radiated, or at least prove that it is primarily radiated. And we can do that by analyzing the temperature and heat flux data. So the testing overview of the temperatures, we used a cross 8 feet wide, 6 feet tall, placed within the burner, and this was just to determine the region within the burner that meets that 800 degrees Celsius requirement. In the bottom right corner, you can see this cross instrumented with 48 thermocouples placed within the burner. Again, the side shields are missing from this picture so that you can see the grid better, but during the testing, it was present. They were present. Here we see the temperature measurements. The two temperature fields shown in the bottom are those two orthogonal planes. And you can see that a large volume within that burner meets the 800°C temperature requirement. So this represents a volume 8 feet square and 6 feet tall once you extrapolate out. So we have a large volume that meets this 800°C requirement. On the left, you see a square meter for reference, so you can envision an ordnance item. Many of them are smaller than a meter, so they easily fit within our burner volume. Additionally, we looked at the coefficient of variation of the temperatures, which is simply the standard deviation of the temperature field divided by the mean, and this is an indication of uniformity. And our target for that was less than 10%. We got a value of 8%. So what this really means is the temperature is uniform throughout the volume. We don't have some hot spots and cold spots, but it's all more or less the same temperature. Heat flux is a little more difficult than temperature because it's not a thermodynamic property of the material, but rather an energy flux through an area. So to measure that, we had to use a heat flux sensor. We used what we call a directional slug calorimeter, and this is essentially a thick-walled stainless steel hollow cylinder that is divided into 4 quadrants. By measuring the temperature of those 4 quadrants, we're able to determine the heat flux into each one of the quadrants. And this gives us the total heat flux in the units will be kilowatts per meter squared at each location. It's important to explain exactly how the heat flux data is analyzed and displayed. This slide shows how we analyze that data. The directional slug calorimeter provides heat flux signals in 4 directions in time. So this plot on the bottom left, the 4 traces are the heat flux signals that are obtained from the gauge in time. We then we look at thermocouple data to determine when the 800°C requirement is met, and then average that data for 20 seconds to get 4 average values. So for this test, the average heat flux on top of the gauge was 101 kilowatts per meter squared, for instance. We then average those 4 averages to get an overall average at that location. So in this case, the average would be 115 kilowatts per meter squared heat flux to the gauge at this point. Then additionally, one other thing we look at is the directional uniformity, which is simply again, the coefficient of variation of those 4 original measurements, so the standard deviation divided by the mean. And that gives us an idea of how uniform the heating is coming in at this location. A high value implies that all the heating are very similar, and a low value would imply that one, say the bottom, is getting much more heating than the top, for instance. And so we wanted a value of at least 75% to show we had good uniformity. The directional subcalorimeters were much more expensive, obviously, than just simple thermocouples, so we couldn't instrument a full volume like we did with the temperature measurements. So instead what we did was build this stand that held 4 directional subcalorimeters at once, and then move it around the burner and do multiple tests. So we would basically do 1 rake at a time, and the goal is to determine the region within the burner that meets that 80 kilowatts per meter square requirement. And so the heights of the 4 gauges were the same heights as the thermocouples. So these will replace, or we measured the heat flux at all the same locations that we measured the temperature. So that's a little confusing, so a little more detail on that. The test 1 there on the right shows 1 vertical rake. So that 1 test measured heat flux at these 4 locations. We then would do a second test and move it over. And so we only measured the heat flux at the location shown by these red circles. We were able to do that instead of moving it everywhere within the burner, because the symmetry of the temperature field also implied a symmetry in the heat flux. So we only measured 1 quadrant, and then we can assume symmetry and flip it anywhere else we need. So on this side we see the results of our heat flux measurements. Again, our target was 80 kilowatts per meter squared, and you see that a large percentage of the volume that we measured met that requirement. Again, we have a 1 meter square block for reference. Also, the large values of the heat flux relative to the velocity of the gas within the flame implies a high percentage radiation, because there just isn't enough gas velocity to produce very much convection. So we have pretty high heat flux values. So while we can't quantify the percentage, we know that the majority of the heat flux is from radiation in our burner. This slide shows the directional uniformity at all the same locations. So each place that we measured heat flux, we could also calculate a directional uniformity. And again, we wanted to be greater than 75%. So you can see a large portion of the burner volume reaches that value. And the top right-hand corner that is low, the reason for that is most of the heating came from the bottom and the left side, and the top and right side were more or less outside of the flame. And so that's why they would show a low uniformity. Whereas in the middle of the burner, you have flame completely surrounding the item, the gauge in this case. And so you're getting heating from all directions, and you have a high uniformity. This also helps us show that we have a high percentage of radiation, because if it was primarily convective, if we had torches on the bottom, we would expect most of the heating to be on the bottom of the gauge and then less heating on the sides and tops. So again, we can't really quantify the percentage radiation, but we can say that we have a majority of heating by radiation. So a summary of the thermal testing. We have designed a propane burner that meets our thermal requirements. We've shown that we have a large volume that is greater than 800 degrees Celsius. We also have a large volume that has a heat flux greater than 80 kilowatts per meter squared. Most of the region within the burner has uniform heating, both from heat flux, from a directional uniformity standpoint and a temperature uniformity standpoint. And we think that the majority of the heating does come from radiation. So with that, we will start our first Q&A session.
Great. Thank you very much, Dr. Hubble. I'd like to remind everybody to submit their questions by using the chat box on the left-hand portion of your screen. And we have received a number of questions. Let me start by reading the first one. Dr. Hubble, it's, could a burner be constructed that used natural gas instead of propane?
We don't doubt that one could be constructed that uses natural gas instead. The challenge with natural gas is it can't easily be stored as a liquid, so the fuel delivery would be the biggest problem with that, trying to supply enough gas to the burner to get the fuel-rich flames that would be required to get the radiation that you need. And it can't be stored in a tank and transported near as easily because of its very low critical temperature.
Right, right. Good. Well, there's some other questions coming in. Next one is, where did the 80 kilowatt per square meter heat flux requirement come from?
Yes, I didn't really have time to get into that. We did, over the last 4 years, we've done many tests in different propane and liquid pool fires, and we've presented those at the Fuel Fire Experts meeting, and that has been a topic of a hotly debated topic at these meetings. But that is the value that was decided upon by the Fuel Fire Experts in these meetings after analyzing the liquid pool fire data.
Okay. Has anyone measured the temperature and heat flux in conventional pool fires? The story is how to deal with the varying wind and other external parameters in influencing the data.
Yeah, as I just mentioned, we have measured the heat flux and temperature in a variety of liquid pool fires. That is where that 80 kilowatt per meter squared came from. And yes, wind is the biggest influencer of those fires for sure. And there's no way around that from what we see. Wind definitely pushes the fires around and changes the temperature and the temperature profile within the fire as well.
Right. So another question, is there a displacement of the propane gas during a fast cook event caused by the explosion energy release that results in loss of uniformity in burn conditions or deviation from expected real-world conditions? And if so, how could this be accounted for in the tests?
Dr. Washburn will show a video where we have our propane fire going and we have an explosion of a mortar. Typically, those reactions occur so quickly that the propane gas quickly reestablishes the flame before you can even tell anything's happened. The only thing we haven't tested yet that I think might influence something like that would be a slower reaction, like a large rocket motor or something. Those are tests that we have scheduled, but we haven't performed yet. So it would be interesting to see how a longer duration reaction that filled a large volume of the burner would influence our flames.
Great. So another question here is by stacking the flux gauges on top of each other, is it possible that heat is transferred preferentially to the lower gauges and the actual heat fluxes of the upper gauges are actually higher than measured or reported?
We don't think so. They're not that close together. They're about 18 inches apart, so you could calculate the view factor from one to the next, and it would be very small. From a radiation standpoint, they really don't see each other very much compared to what they see in the flames. And also, our flames are quite opaque, and so they're pretty optically thick in that distance between the two. So there's no good radiation path from one to the other. There's too much flame in between them, if you will. So we don't think that we're getting much influence from one gauge to the next, just based on their size. They're relatively small compared to the distance between them. I guess would be a better way of answering that.
So a simple question here, how much fuel is used during a typical test?
Again, Dr. Washburn will give actual stats, but typically the burner that I showed there uses about 20 gallons of propane per minute. So it's completely dependent on the length of your test, but some items that we test react in less than 2 minutes. So you could be as low as 40 gallons of fuel. I mean, some items take 15 minutes, so 300 gallons of fuel. But those are sort of typical numbers. 20 gallons per minute is pretty much what we're using right now.
Let me ask you a question from my own curiosity, since this is not a field that I work in. This is Mike Cavanaugh talking. Is there an international perspective on this problem as well? I mean, are there some international standards or approaches done by others that would be modified or changed by the results of this work?
There's certainly the STANAG 4240 that I mentioned at the beginning is an international agreement, and that is the purpose of the fuel fire experts meetings, is to come to an international agreement on how to define these burners, how to calibrate them, and sort of share information between the countries on what we have tried that has and hasn't worked. And so there's been a number of ideas out there. We've sort of stood on the shoulders of giants, if you will. They got the head start on us, but we were able to work off of what they did and develop this system from their past successes and failures.
Great. Good. Well, with that, there's still chances for everyone to pose additional questions for Dr. Hubble, but let's move on to the next, and Dr. Washburn will take it from here.
Thanks, Dr. Cavanaugh. Thanks, Dr. Hubble. So, going on from what Dave was talking about, there are hundreds and thousands of ordnance and munition items that could be tested in these propane burner. From a realistic point of view, there's no way we can test all of them. What we did, a lot of our focus was quantify the burner. What's the heat environment that the items will see? Once that we can quantify the burner and say this is the same as a pool fire, we therefore go with the assumption and therefore items will react the same in both the pool fire and the propane burner. Also, though, we wanted to do some examples just to make sure that our assumption is correct, and that's what I'm going to report on here, is that once we quantified the burner, the heat temperature, the heat fluxes, we were ready then to put some items there and see what happened and compare them with pool fire. We also did some tests with inert items, and the purpose of there was just to see what would happen when a large inert item was there. So first is a large aluminum container. So this is 500 pounds of aluminum used to house a large munition. It's over 7 feet long, almost 3 feet high, and it was the largest thing we've ever tested in a 12-foot by 12-foot burner. Some of what we wanted to see is what would happen if we put something that large in a burner. How would it affect the flame? And also, knowing that the aluminum should melt, what's going to happen when we have all this large inert items flowing over the pipes and maybe preventing the burner from working? So, as you can see here, you see in the middle, it completely surrounded the container. It enveloped it, and also too is that around the container we had 12 thermocouples, and they all were above 800 degrees Celsius. So there was plenty of heat to both surround and heat up the item. All 500 pounds of aluminum melted within 3.5 minutes. And what happened is that the burner was able to function. We don't have a picture here, but you can see the item in that center picture where it's before it's melted, soon after it melted, and the flames went on just fine. Even after it melted, when we have our little candles coming out of the pipes, they were able to penetrate the molten aluminum. One thing we did here too is that we put sand on the bottom of the burner, and that led to pretty quick cleanup of the burner, and we could use it right away. So moving on to actual munitions, ordnance items, what we started with first were some 81 millimeter mortars. And we found a mortar that had 2 explosive fills. The first one I'm going to report on is the insensitive fill. It had IMX 104, which was specifically made to have a low reaction. So for fast cook-off, testing. There's they rate on how this item reacts from a 1, which would be a detonation, catastrophic event, to a 5, where it will burn, but it stays where it's at, and it really has no, doesn't send anything outside of the pool or burner itself. And so this IMX 104 is slated to have a Type 5 reaction. It was previously tested by the Army in New Jersey at Piccadilly Arsenal in a kerosene pool fire, which made it convenient for comparing our results with the propane burner. And so what we want to do is be able to replicate what happened in the kerosene pool fire in the propane. And on where you can see there, you can see the schematic from the test setup from the kerosene, and on the right you can see our test setup, photo of our test setup. So the results of both the kerosene and propane was that it had a Type 5 reaction, or it just basically burned within the area itself, the pool fire or the propane burner. Now, as Dr. Hubbell was talking about, there's a large reduction in fuel usage. So the kerosene used almost 3,800 liters of kerosene, where we used about 570 liters of propane. So that's a significant savings in cost. So maybe you could buy propane for $3, and same with kerosene. But at the same time, too, sometimes there's additional cost for sometimes our kerosene, depending on our supply chain, can be up to $6 a gallon for the kerosene. So an easy thing here is that the propane burner, the item did not have a vigorous reaction. However, we didn't really have to do anything. You can see it kind of coated the pipes. You see on the right picture, you see the pipes are kind of white coated. We just tested again after that, and it didn't have any problems. So as I stated, the same mortar item that had the IMX 104 explosive fill also had composition B explosive fill, which was expected to have a violent reaction. Now, what we wanted to do then is compare with some kerosene data, which there was, that had been tested there at Dahlgren previously, and they are in a slight orientation. The kerosene pool fire had been on a horizontal orientation, and whereas we had vertical, and the reason why we kept vertical is we wanted the same test site as the IMX 104 explosive field testing. So the result of the testing, as you can see, is that in both of them had a violent reaction. So it was not a detonation, but definitely there was an explosion. There were shrapnel that went out, or fragments that went out, damaged the pipes, and but once again we used significantly less fuel, and there were 3 pipes that were damaged, but it took less than 3 hours to unscrew them and put in new pipes. Now, a key thing here is that we use significantly less fuel in the composition B explosive fill testing than we did with the IMX 104 explosive fill testing. The reason why is because the composition B had a much more vigorous reaction. We knew when it happened, and so we had a much better idea of doing that 150% pass reaction. It's one of the advantages of propane. You can shut it off. And so if a test goes quickly, you can go past the 50%, and you're able to finish out the test and use less fuel. So here is a video that shows the test with IMX with composition B. So I don't know if it started yet, but
It's playing on my screen.
oh, is it? Okay, good. There it goes. Now it goes on mine. Good. So I don't know if we're, as you can see on my stream, it's just starting to ignite. You can see the test item there in the middle that it's standing vertical. This is actually one of our, this was near the beginning. We have much better ignition now, but that definitely fell within the standard 4240 as far as ignition transient. So, but here this is a good wind test, a nice buoyant, radiant flame, and this was great as far as the wind goes. On my screen, it just went off, and as you can see, it kept on going. So we had that violent reaction. It damaged 3 pipes, and we proceeded to have our fire go. So here is some stills. The sequence is in 3 seconds. It just it's capturing the explosive event where it damaged the 3 pipes, and even after the explosive event, it was we had our nice radiant engulfing fire. So as I talked about, one of the advantages of propane too is its ability to have a very consistent and quick ignition process. Down below you see this was a further test for another item, and we tested both in the fuel fire and also in the propane burner, and there's 2 seconds, 10 seconds, 20 seconds, and 40 seconds after the ignition event. Propane fire had a consistent fire almost immediately, as opposed to the pool fire, which is kind of a gradual ignition process. Once again, too, this just really qualitative. You can just see the difference in the environmental emissions there. That pool fire there on the top right, just that huge cloud of black smoke. And then down and below we have our nice radiant orange fire, which is very radiative, but it doesn't have the inefficient soot coming out of it. So here I'd like to quantify some more or show some more explosive ordnance tests that we performed. So we performed a test on a 105 millimeter artillery cartridge, M1 cartridge. It had an inert warhead, but it had a live propulsion system, and it was packed in the shipping container. And with this one we tested both propane and liquid pool fire test. So the results of the test for in the liquid pool fire, there was varying results depending on when the test was taken. This happens in fast cook-off testing with large, buoyant, turbulent flame, heat conditions. There are some differences in reactions, even within the pool fire itself. However, you can see with the propane burner, when we had similar type of heat environment, flame temperature, we had similar reaction times and reaction assessment. And so it's important to realize that if you just take one fast cook-off test in kerosene and one test in propane, they should be similar. They won't necessarily have the exact same reaction, but that's just because it's the same that you would get in a pool fire itself. So, but here we were fortunately able to have multiple reactions within the pool fire, and they had the same reaction with your propane burner. So here is another 2.75 warhead. It was also tested within a container. It was tested in both the liquid pool fire and propane burner. And once again, we have same reaction assessment, different reaction times. Once again, that's kind of similar to what you get in a pool fire. Reaction time isn't something that's required to be consistent. However, the most important thing is the reaction assessment was the same between both of them. And once again, we used significantly less fuel, almost a tenth of the fuel we used for the propane burner. Okay, here, and this one here is an a low-weight anti-armor weapon, and we didn't necessarily have direct comparison with the fuel fire test because the item that was tested in the fuel fire had a live warhead, and ours had an inert warhead. The reaction time that I'm showing there is the reaction of what we assume was the propulsion part of the artillery, of the lightweight anti-armor weapon, and the initial reaction was similar. The overall reaction was different in the sense that one had a warhead and the other didn't, but the time for the propulsion side and its reaction were the same as far as that goes. So here is a summary of the testing we've done up to date. We're going to do larger items. This is what we've completed at this point. Key thing here is that pretty much we get the same reaction in the propane burner as we do in the liquid fuel fire test. So you can use past results for your weapons, your ordnance items, and compare them with present results in the ordnance in the propane burner. One of the requirements for munitions is that they improve their IM signature, their incendiary munition signature, and so they need to be able to base current results and show against past results to show that improvement. You can do that with the propane burner. Another key thing here is we have the same temperatures. Average flame temperatures are very similar in the ballpark as far as that goes, as you would see in a liquid pool fire. And as far as money savings and emissions reductions, our fuel reduction is significant. You know, up to 10%. We need 10% of the fuel. So as far as testing in larger items, one of the things we're doing is we built a burner that's a 10-foot by 20-foot burner. This was built at a different site, so it can be transferred to a different location. It was actually built in the same area that they do the jet fuel fast cook-off testing. As you can see, you see that dirt berm. That's where they would put the liner down and pour the fuel in to do the actual jet fuel pool fire testing. We can remove everything, all the burner apparatus you see there is currently, we can remove that very quickly. I think it takes like 15 minutes forklifts to remove that, and we could do either testing, and the firing system is set up that we could do either testing depending on where we go with that. We are currently characterizing that burner. I will be presenting those results at 2016 Incendiary Munitions Energetic Material Technology Symposium in Nashville next month, and same with Dr. Hubble and Dr. Goulet at the EPA did some testing with the emissions, and they're going to be reporting that at that symposium as well. But if we go to the next slide here, we can see some results when we were. You can see the burner setup, the heat flux gauge setup that we had at Dahlgren. You can see right there in the middle of those flames. But once again, we have our large, buoyant, radiant flame engulfing our items and providing that thermal environment that's the same as our liquid pool fire test. So right now, what we've done is we've tested in an 8x8, 8-foot by 8-foot burner, a 12-foot by 12-foot burner, and a 10-foot by 20-foot burner. We're currently also building a 15-foot by 20-foot burner at Channel Lake just to scale it up even more. And each of these burners, we've been able to get that consistent, radiant, buoyant flame that you need in order to have a valid test. And part of this process is we're looking to transition this burner to other sites and be able to have other people use this as far as their testing goes. So as far as standardization, Dr. Hubble talked about this. So first of all, in the United States, the U.S. Joint Services and Incendiary Munitions Technology Panel, which has kind of a technology oversight over incendiary munitions for the Department of Defense, has unanimously endorsed this overall effort. They are currently working with us to support this through both OSD and the JROC, the Joint Requirement Oversight Committee, to make this approved for U.S. use for scoring within this next fiscal year. Also, we're working with STANAG 4240, rewriting the AOP 4240 that would allow propane burners. This is going through approval process, and we're hoping that soon that will be approved as well. And we have submitted a patent on this technology, which is currently going through its process as well. So as far as conclusions, as I emphasized at the very beginning, there's no way we can test every single munitions item. So what we've done is we've shown the fire is the same in a pool fire and in this propane burner. Therefore, we can put in different items and you're going to get the same reaction. Up to this point, we've done a small number of items that we've been able to receive, and then also had pool fire data that we compare against, and in the items we've tested so far, they've had the same reaction as they did in the jet pool fire. So this propane burner really is an environmental alternative for fast cook-off testing, and we've already transitioned it to 2 sites, 2 different types of firing lines, 2 different types of setups, gone from a wooded area to a desert area, different locations, and both of them have been successful in transitioning to those sites. So I think that's the end of where I'm at right there, and we're going on to the next question. So here's for additional information and Dr. Hubble and my contact information.
Great, Dr. Washburn. Thanks very much, both of you, for very interesting talks about a very interesting technique for doing this test. This opens it up for our second Q&A session, so let's dive right in. First one is, will the ordnance reaction always be the same between the propane burner and the liquid pool fire?
Right, and that's a great question. So within the normal variance within a pool fire, you're going to have that variance between a propane burner and a pool fire reaction. However, within that variance, yes, they will be the same.
Okay. Good. What would happen if there's a large detonation event, which I assume means potential destruction of the burner?
Right. So we recognize if there was a large detonation event, and in our where we had the 81 millimeter that exploded and damaged the pipes, it didn't catastrophically destroy our burner. So at that point, there is a good possibility that your burner would therefore not produce a very regular flame. As far from a safety point of view, all of our burners so far have valves, cutoff valves right at the propane tank that are protected behind that would shut off, and you wouldn't have to worry about propane spilling out or anything like that as far as an environmental or safety hazard. So if you were to have that event, you would damage the ability to continue on the test. One of the thought processes there is if you had that event, you've already failed your test. And so pretty much at that point it's a 1, and that's further reactions wouldn't really change that reaction assessment for your item.
Mm-hmm. And you had several groupings of reaction assessments that may be familiar to the folks working in this field, but can you elaborate
Sure.
a little bit on the different what the meaning is of the different
right.
numbers or
right. So like right. So a 5 would be a burn reaction. A 4 would be a burn reaction, and where you have some type of propulsion, where either the item itself moves or a component of that item moves. I think it's I apologize, I don't remember the exact distance, but it will move a certain distance from the burner. When you get into type 3 and type 4, those have to do with where you've had a pressure buildup, and you'll have a type explosion, and then type 1 is where you have a detonation, and so you have supersonic burning of your energetic material and blast waves associated with that.
Okay, great. Well, this may be a good segue to the next question. Have you ever tested items with multiple explosive subsystems where the first reaction in one of them might destroy parts of the burner, and if that happened, did the burner continue to work so that all reactions could be completed?
Right. Yes, that is something we've thought about. We have not tested one of those yet, and we need to do that. That's part of our testing that we want to do as far as next year goes. We have tested items where they had multiple reactions, but not where one of them damaged the pipes that we could keep on testing. Some of it would have to be the level of damage. So with the composition B filled 81 millimeter mortar, our assumption is that was a violent reaction, and if there were further subsystems within that reaction, we could have kept on testing those because the flame was still regular and fine after that point. So there would reach a point if we damaged it too much the burner too much that it would prevent really characterizing future subsystems characterization, and that would be one of the limitations. However, once again, if it was too large of a reaction, you already have a type 1 at that point too, and you've already kind of failed your test.
I see. Okay. Do you expect, or have you measured heat flux variations for different propane burner densities? It looked like the 12 by 12 or 10 by 20 burner had a different burner or orifice density in the information you provided.
Right. Yeah. So we did measure heat flux. So and we're going to be presenting that at the IMEMTS symposium, and the flame. So both of the heat fluxes, both for the 12 by 12 and the 10 by 20, were both above 80. The 10 by 20 were larger, maybe 20% larger, but they were definitely not. They're definitely within what had been measured previously in fuel fire tests, and some of our assumption is it's just a larger fire, so it's going to have higher heat fluxes.
Great. Okay, the next one is, can the data or the models from the 81 millimeter item testing be extrapolated for larger items?
Right, yes. So hopefully, so some of it is we haven't had the opportunity to do a lot of modeling and simulation of these tests. A lot of ESTCP focus is obviously getting the prototype up and running and getting the validation data, but I think that's a good comment in that, you know, some further kind of continuation work to do some more in-depth kind of analysis of those tests could maybe use for some scale-up and also for some analogy type tests between ones. And so we haven't done that yet, but that would be a very good thing to do in the future.
All right, good. So you're getting some good ideas for future tests.
Yep, for sure.
All right. Next one is, how far is the propane tank from the test site?
Right. So it depends. And I apologize for Dave, but I think it's like, is it a 100
At
yards?
Dahlgren, it's about 200 feet.
200 feet, okay. And it's about 400 feet to the one at China Lake. And the one at China Lake is behind a large concrete wall too. Just they happen to be there. It was that they use it for the fuel fire test. So ours is probably double the distance as the Dahlgren distance.
Okay. Here's a detailed question about the type of items you can test. It says, how would you fit a test A-frame between the pipes?
Right, and so and we've looked at that, and so we've done some testing that had large spacing between the pipes that would put an A-frame right in there. And as Dr. Hubble talks about, we need that heat feedback to kind of get our continuous flame, and we didn't get that. And so some of what we've done is we've devised a test that has devised a burner that has closer spacing, and then at the points where you would put down the A-frame feet has longer spacing that you would put the A-frame in there, and then you'd be able to hang the item from the A-frame. So we've designed, and the China Lake burner actually had that designed into it.
Excellent. Another question is, what other types of munitions do you plan to test as part of the project?
Right. So we would like to test a large bomb. We'd also like to test a large warhead. We are also going to, we are going to test a large bomb. We are going to test a large warhead. We are going to test a rocket motor to get some of what Dr. Hubble was talking about. We're also going to look at maybe intumescent paints to see, or different coatings to see how it affects the difference between the different types of testing that we're doing. And also maybe what the question that was talked about, test an item that has multiple reactions and that we know that are going to happen, and then see what happens in that process.
Okay, good. And again, just for those of us not working directly in this field, is it fair to say that what you're trying to do at the end of the day is improve the protection in the explosive items that will withstand these fires, so that the potential for many explosions to occur will be reduced, but not, I presume, completely eliminated.
You are absolutely correct. So the idea is for the ordnance item to, at the right moment, to do what it's supposed to, and then in a hazard situation where it has a thermal insult that's not expected, that it will not react violently and hurt those that are handling it.
Yeah, good. Okay. Well, that's enough, I think, questions for you, Dr. Washburn, directly. I think we can join forces with your colleague here, and either one of you, I think, can respond to this. The question is, who has authority to accept or approve the alternative test, presumably your propane burner versus the pool test, and is that approval based on specific ordnance items?
So, as for the United States, the one that would make this test an official test for scoring would be through the OSD and the Joint Requirements Oversight Committee. I think that's what JROC stands for. And at that point, they would give authority that this test could be an acceptable method of scoring munitions for fast cook-off. And then at that point, location could then decide which type of test that they would use. And then I think DDSB, or no, each of the service, DDSB does the hazard classification, and then each of the services have different incentive munitions panels, and also the Joint Service Incentive Munition Technology Panel are participate in actually scoring these tests, and so then they would take the propane test and score it on what they, using their methods of scoring.
All right. Dr. Hubble, do you have anything to add to that?
I think he pretty much summed it up.
Okay, good. Okay. The next question is, do you have any plans to design a modular system that can be easily transported by truck between different test sites and be set up relatively quickly?
I think that was a part of the design of the China Lake burner specifically, was its modularity and ease of adapting. Theirs is a little easier to change than what we have currently at Dahlgren, since they don't have a frame that it fits into. Would you say that's correct, Ephraim, since you all have to move yours in and out for each test?
Right.
So yours is much more modular than ours. We have a permanent site set up for ours, and they share a site.
And a nice thing too is that this we've been promoting and presenting this technology, and I think Beaufort's test range has a modular one that they can put in a truck and take around, that they've designed that's similar to ours. So I think some people have already kind of come up with that and are doing that as well. So.
All right. The question here is, do any other burner designs in the world meet the requirements of 4240?
I suppose as Ephraim just mentioned, the Beaufort's design from the brief I saw presented at the last IMEM does meet the 4240 requirements. I think also the Meppen burner that Germany operates would meet these requirements.
Yes.
All right.
Those are the only two I'm aware of.
Good. Here's a couple of questions along the lines of the environmental benefits of your proposed method versus the pools. Have there been any difficulties obtaining air emissions permits for the FCO assessments using the liquid fuels, and if so, do you anticipate an easier process using propane?
From the China Lake point of view, yes. We have to monitor our air permits every year, and then definitely keep track of how many pool fires that we can do. This is Dr. Hubble and our colleagues at EPA did some testing recently. to demonstrate quantitatively how much our emissions are going to be reduced, and definitely this will help us be able to do more fires. And as in the future, when it gets more stringent, it'll just help us even more. I don't know what your perspective there at Dahlgren is, Dave.
Yeah, I agree. And once that paper is published in the next month and a half or so, I think that data will really help our case, like Ephraim said.
I mean, this is Mike Cavanaugh again, but I'm assuming that pool fires produce a lot of particulate matter, and much less so from the from the propane burner. Not to mention the reduced fuel usage.
Yeah, our data showed a 150 times reduction in PM 2.5.
Right.
So,
yeah, seems to be a no-brainer. Good. If somebody has a desire to use one of your burners, how would they get one to their particular site? What's the process you have thought through on that one?
As part of ESTCP, we're going to generate a report that will be accessible to anyone that will detail the burners that we built, and also the process we use to calibrate them, and that will be open to anyone, and they can contact Dave, Dr. Hubble or I, and we'll give them, we'll send them to you. Also, too, is some people have already used some of the papers that we've already published to kind of start designing their own burners. Those are already out there in the literature. You can use those, but obviously we want to help facilitate this going out, and we're more than happy to do that.
Great. I think this was just answered by David, but let me ask it again. Have you performed testing to quantify the emissions reductions from your propane burner compared to a liquid pool fire? And maybe you could describe what emission factors that you're actually measuring.
yeah, we did do that testing, and we don't have all the results yet. And so in the paper I'm presenting, the main things that I quantify are the reductions in particulate matter, carbon monoxide, show of burning efficiency, and the volatile organic compounds. And in all cases, the reductions were at least 80%. In some cases, the reductions were, more than 99.8%. So, like I said, the particulate matter 2.5 and smaller was reduced by 150-fold, and something like toluene and formaldehyde and some of those compounds were all reduced by at least 90% in the propane burner.
Great. Okay. Another question is, what is the cost of the burner relative to the traditional setup?
Dave, you want to answer that? You've done some of this.
Trying to. It's hard to quantify what the cost of the traditional setup is. At China Lake, the traditional setup's pretty cheap.
Well, I mean, but from fuel, it's expensive, right? So that's where the cost savings come. So
yeah, it's really the operation cost is where you save money in the long run. A fuel basin is relatively inexpensive to construct, that you can just pump fuel into, but it's the long-term operational cost is much cheaper.
So I hate to put you on the spot, but it was like $5,000 for the expendable part of the burner. Was that how much it was, or was it less?
Yeah,
than that?
certainly in that magnitude.
Right. So it was like $5,000 if you completely wiped out the part that's accessible to a reaction. It would be $5,000 if you had to replace it every single time, and we haven't had to do that. We haven't done a reaction yet where we wiped out the burner. We have more than $5,000 savings in fuel costs every single time we do a burner. So even just in fuel costs, we paid for the burner every time we do it, and we use the burner multiple times.
And I would just add that as munitions get safer and safer, the likelihood of the very violent reactions decreases. So we're having less and less reactions that would completely wipe out a burner as time goes on.
So I might add, you could undertake a sustainability assessment of the two different methods and also show the significant advantages, even though it might be, from a life cycle point of view, somewhat more expensive.
Yeah, it certainly has a return on investment, on the order of 3 years or less, depending on how many tests you perform annually.
Great. That would be, yeah, go ahead.
No, go ahead. Sorry, Dr. Kavanaugh.
Well, I just wanted to ask, keep the questions going here along these lines. Have you done an analysis to quantify the greenhouse and other atmospheric emissions of the two methods? So I guess that would be another emissions comparison have you done that?
So I looked in there from a CO2. You measured that, didn't you, Dave?
Yeah, the CO2 is going to be about the same per mass of fuel burn. So your big reduction there is just that you're burning so much less fuel.
Right. Yeah. So the CO2 in of itself will be the same per mass, but we're a tenth of the fuel. So I guess a tenth of the greenhouse gas emissions.
Yep. Well, you could throw in a cost of carbon, and even though that's controversial, you could use that to also compare the two methods.
Right. Another factor that doesn't necessarily come out directly in dollars is that the test personnel that work in the propane and work on the pool fire, they like the propane. It's not stinky, smelly, yucky, all that kind of stuff, as opposed to you have this large, 10-meter pool of jet fuel that's just, you get a headache and all kinds of stuff while you're working around with it. Propane, like Dave talked about, you don't have any fuel until everyone's gone. And so there's a lot of maybe things you can't necessarily quantify, but are very big advantages to this.
Good. Kind of sticking to the environmental theme, this is actually getting back to some of the details about your technique and the equipment being used. Does the directional slug calorimeter require calibration prior to deployment for testing the burner?
We have not been calibrating it. It is based on first principles, so the calibration and the errors associated with that stem straight from a thermal analysis of the gauge itself and not from a direct calibration.
Okay. So one last one here. Is there a target date for replacing the liquid pool fire testing technique with the burner testing?
So as far as date, transitions as far as having no one do pool fires, that will take some time, and I don't think we necessarily know when that's going to happen. As far as having propane be acceptable and that you can score it, what we're working towards is fiscal year 17, next year, and that a site that wants to use the propane burner to score a fast cook-off would be able to do that, and that's kind of what we're working towards.
Very good. I think what we'll do at this point is I'd like to thank both of our speakers, Dr. Washburn and Dr. Hubble, for a really excellent presentation. I want to remind everybody that at this point there's another webinar coming soon. You know how to contact both of our speakers, so if you have any additional questions or issues, certainly contact them directly. The next webinar is September 8th on the assessment of redox-based groundwater remediation technologies, and both of the speakers are excellent from Colorado, the Oregon Health and Science University, and the registration is open for this webinar, so please visit the website to participate in this and future webinars. And then before we conclude, there is a survey reminder that will come up, and so a copy of the presentation of today's session will be archived on the webinar web page in case you'd like to refer to it in the future. And we'd really appreciate it if you would take a moment to complete the survey that will pop on your screen at this time. So I think with that, we'll conclude today's webcast, and thank you all for participating, and especially our speakers.
Thank you.